Picture two programs solving exactly the same problem. One performs almost 50 million comparisons. The other needs about 10,000 lookups. Same input, same answer, the difference is one idea. In TwoSum, an interviewer gives you an array and a target. You return two different positions whose value add up to the target. Let's say the array contains 2, 7, 11 and 15 and the target is 9. You can immediately see that 2 plus 7 works. But when the correct pair is not sitting right in front of you, how do you avoid searching through every possible combination? That is what we are going to build. Not a solution to memorize, but an instant you can reuse. Before we write any code, let's try the problem ourselves. Say the array is 2, 7, 11 and 15 and the target is 26. Which two number would you choose? Start with the first value. What would you check next? Notice how your eye choose one value and then scan the value after it. Take a moment and predict the answer. 11 plus 15 gives us 26 at the position 2 and 3. Your brain moves through those candidates almost automatically, and a computer cannot. Every comparison must become an instruction, so let's turn that first instinct into a code and count the work. The most direct solution uses two loops. The outer loop chooses one value. The inner loop checks every value after it. Starting one position ahead means we never repeat a pair or pair an element with itself. For our target of 26, the computer checks 2 plus 7, 2 plus 11 and 2 plus 15. Then it tries 7 plus 11 and 7 plus 15. Finally, 11 plus 15 gives us the match. That is 6 possible pair for only 4 values. And this solution is correct. A simple correct solution is always better than the clever broken one. The weakness is that brute force has no quick way to ask, is that exact partner I need available? It must keep checking one candidate after another. With 4 values, 6 comparison barely register. But suppose the array contains 100 values, now there can be 4,950 pairs. At 10,000 values, that jump to 49,995,000. The exact count is n times n minus 1 divided by 2. In big O terms, the growth is big O of n squared. The curve is what matters. Double the input and the work becomes roughly 4 times larger. Brute force can still make sense for tiny input, strict memory limit, or is a correctness baseline. But when the input can grow, we need to replace all the searching with something we remember. Now, let's change how we think about the problem. Instead of searching for the second number, calculate what it must be. If our target is 9 and the current value is 2, the missing value has to be 7. We call that the complement, target minus current. Now walk through the array from left to right, keeping a map of the value you have already seen. At each position, ask, have I already seen the complement I need? If yes, you have the pair. If no, store the current value and its position, then keep moving. The source had changed direction. Instead of looking forward through every possible partner, we calculate one exact partner and check our memory. Now let's walk through another example. Suppose the array contains 3, 2 and 4 and the target is 6. We begin with an empty map. At position 0, the current value is 3. 6 minus 3 gives us 3. Have we seen a 3? Not yet. So, we store 3 at position 0. At position 1, the current value is 2. 6 minus 2 gives us 4. We have not seen a 4. So, we store 2 at position 1. Finally, at position 2, the current value is 4. 6 minus 4 gives us 2. This time, 2 is already in map at position 1. So we return position 1 and 2. Here is the important rule. Before we process any position, the map contains only value to its left. That guarantees two different elements without scanning anything to the right. Now pay close attention to the order of two operations. We check for the complement first, then store the current value. Why does that matter? Suppose the array contains a single 3 and the target is 6. If we store first, the algorithm could match that 3 with itself. But the problem requires two different positions. Now, suppose the array contains two 3s. At the first one, the map is empty. So, we store position 0. At the second one, we look for the 3 and find the earlier position. Returning 0 and 1 is valid. So, checking before storing prevents self-use while still handling duplicates. The same code works with negative values. Negative 3 and the positive 3 can combine to make 0. And if the solution is not guaranteed, we return whatever empty result the application expects. That is the difference between understanding the code and simply memorizing it. So, what happens to the complexity? With a well-behaved hash map, insertion and lookup take expected big O of one time. We perform at most one of each per value, giving us expected big O of n time. The map may store every value, so the extra space is big O of n. The word expected matters. Hash map can have collision and theoretical worst case dependent on implementation. But expected big O of n is the standard interview analysis. Could we sort the array and use two pointers? Yes. That takes big O of n log n time. But sorting changes the order. Because toSum asks for the original position, we must preserve those indices and may need to avoid mutating the inputs. So, for an unsorted array where position matters, the hash map is usually the cleanest trade-off. Not because memory never matters, but because direct lookup fits the requirements. toSum is no longer just about adding two numbers. The deeper idea is replacing future searches with information we save now. Whenever a problem asks whether something exists, whether you have seen it before, how often it appears, or whether a matching partner exists, a map or set should cross your mind. Contains duplicate use a set of seen values. Valid anagram and first unique character stores count. Array intersection check membership. toSum often combines an outer loop with a toSum style search. These patterns are related, but not identical. toSum use complement lookup. A frequency counter records how many times each value appears. So, when you face the next problem, ask yourself, can I save something now so I don't have to search for it again later? Let's reduce the entire solution to one simple process. For every value, calculate the complement, check whether you have already seen it, then store the current value. Brute force is correct but quadratic. The hash map uses extra space for expected linear time. Checking before storing prevents self-use while still handling duplicates. So, when a problem asks you to find a pair, do not start by searching for both values. Calculate what missing value has to be, then ask whether you have already seen it. That is the toSum instinct.